Okay. Okay. So, good afternoon or good evening. As I mentioned, so we will. This is a review session. As I mentioned, I received several requests to record this session, and what I so if you have, so I have started recording. If you have any objection, please tell me, because this recording, this session, I will put it online for a few days, and then I will put it offline after the exam. Yeah. So, what we will do today, I will just go probably 5 minutes very quickly about over the topics of the class. I mean, the exam, and then I will solve one entire exam. Okay. I will share the screen. I think you can see my screen, right? Okay. Can you see the screen? Hello?
Yeah, we can see it.
Yeah, because when you in fact, if you answer via chat, I don't see it anyway. So let talk very briefly about the topics of the class. So of the exam. The topics will be of course chapter 24, 21, 22, 3, 4, and the topics will be the calculation of the electric field, of the Coulomb force. This is a usual calculation, like the integration, etc. And then the Gauss law, and then so we will have some examples here with the Gauss law. We will also have some examples with the electric field and the Coulomb force. We have the electric potential. I think this exam will cover, I mean, the sample exam that I will solve will cover everything: electric potential, and also the relationship between the electric potential and the electric field. So how to go from one to the other, and yeah, and then the capacitors. Okay, and then the capacitors. Okay. So this is so basically the capacitors will be capacitors, a normal capacitor and capacitor with the dielectric. Okay. The Gauss law with the dielectrics, I will not include it, so you will not be asked to. I mean, you will not be asked about the Gauss law applied to the capacitor or to the dielectric. Okay, so let's start. Let me see if there are any questions. No, there will be. Okay, so now, so let me give you the format of the exams. So by the way, this exam is a little bit long because it's a 2-hour exam. So basically, you will get 4 problems instead of 6 problems. So this is the format of the exam. For example, in this exam, we have 6 problems, 100 points, there are 12 pages, and then we have these formulas. Now, as you can see, the formulas about the electric field, the Coulomb force, the electric field are not given, because you are supposed to know them. I might give some formulas, but so I might give the formulas with the capacitance. Okay. So if we need them, for example, I know that the capacitance is the charge divided by the potential difference, and then epsilon A over D, the distance between the two, and the area of the two plates, parallel plate that form the capacitor. Okay, so this I can give. It's not a problem. but the formula for the electric field and for the Coulomb force, I think you should know. So and obviously the formula for the Gauss law, it's always it's very simple. The integral of the electric field over the closed surface is equal to the enclosed charge divided by epsilon zero. Okay, so let's start this exam. Let me see if I can make it 200. Okay, so a solid conducting sphere with radius r carries a positive total charge, and the sphere is surrounded by an insulating shell with inner radius r and outer radius 2r. So the insulating shell has a uniform charge density rho. You give all your answers in terms of q and r. Now, so the questions find the value of rho, the charge density of the insulating shell, in such a way that the total net charge of the entire system is zero. Now, let's first look at the keyword in this problem. A solid conducting sphere with radius r carries a positive charge q. So now we have a sphere that is conducting. Okay, this is a sphere that is conducting, that has radius r, that carries a charge q. Now we know that the charge of a conductor is always on the surface. Okay, so the charge will be located on the surface. Okay. The sphere is surrounded by an insulating shell, with inner radius r, so it's a shell. It's like a donut. It's like a donut that you put inside a conducting sphere, and outer radius 2r. So we have a shell, okay, this one. And so this radius is 2r, and it is insulating. Okay, this is insulating. And this charge, or this shell, has a charge density rho. Now, remember what we have said, electrostatic conditions in the conductor requires that there is no electric field inside, okay, inside the conductor. So the electric field inside the blue sphere is zero. The charge on this blue sphere is located on the surface of the blue sphere. And then we put an insulating sphere shell, and this shell has a charge density. Now remember, in the insulator, the charge is distributed within the volume, uniformly distributed. So find the value of rho so that the net charge of the entire system is zero. Now, I know that the charge on the conductor, is positive q. So what must be the charge, the total charge on the sphere, on the shell, on the insulator sphere? Obviously, negative q. Okay, so it's a negative q. Well, now I know that the total charge of on the insulating sphere is negative q. So what is rho? Rho is the negative charge of the insulator divided by the volume of the shell. So what is the volume of the shell? Well, the volume of the shell is this. So, the volume I will write here. So the volume of the shell is the volume of the red shell, the donut. So this means is equal to the total volume of 2r, the volume of the 2r sphere, minus the volume of the blue sphere. Do you agree? Is this clear? Hello? Did you understand this?
Yes, Professor.
Okay, so what is the volume of the 2R sphere? So the volume of the 2R sphere is 3 pi 2R everything cubed, minus the volume of the blue sphere is 3 pi R cubed. Well, we can easily solve this. Well, actually, it will be 3 pi. And then this will make 8R cubed minus R cubed. This will give 7R cubed, which will be 7 times 4 is 28. So 28 pi over 3R cubed. This is the volume of the shell. Are you following? Is this clear for everyone? Okay.
Yes.
Okay. So what? And so now we have everything. We have the volume. What we want the charge. This is the question. Calculate the charge, the volume charge density on the sphere, on the insulating shell, so that the total charge of the system is 0. So we have found that the charge or the surface charge density must be equal minus Q over the volume of the shell. The volume of the shell, we just calculated it, so it will be equal to minus Q divided by the volume. So this will give me 3Q divided by 28 pi R cubed. Okay. So this is the total surface charge density on the insulating sphere. Is this clear? Okay. Now, the second question, calculate. Okay, so you have found rho here. Now I want to calculate the following. Calculate the magnitude of the electric field in each of the following area or regions. Between 0 and R, between R and 2R, and outside 2R. Okay, any question? So what is the electric field inside between 0 and R, capital R, in the blue region?
0.
0.
0, because we are talking about electrostatic conditions for the conductor. So this is very easy. So when 0 R, so the electric field is 0. Now, how are you going to calculate the electric field in region 2? Yeah, so the electric field in region 2. What do we have to use?
We have to use the
Gauss law.
equation.
Exactly, the Gauss law. So the Gauss law tells me that the electric field in that area, the area of the blue sphere, okay, the area of the okay. So let me first, you know what? Let me start a new page so that I can explain. So I want to explain it in detail here. So what do I have? I have, this is the blue sphere. And this is the shell, okay? So this is 2R, okay? It's not in scale, but I just make it bigger so that I can explain. What I want to calculate, the electric field at any point here. This is R, and R is between capital R and 2R. So what do I have to do? I have to take the green surface as my Gauss surface. So the integral E over the green surface dA is equal to the charge enclosed by the system. Remember, by this sphere, remember here I have plus Q. Okay, so what is the total charge? The total charge is the charge in the conductor, and then minus, well, because the other is negative charge, here I have a negative charge. I will call it Q prime. Minus Q prime divided by epsilon 0. Are you following? Is this clear? Did you understand what I just did? If you
Professor,
did
can you
not
repeat it
understand,
again
okay,
one more time?
yeah. So the difference here is that the blue, the red shell is an insulating, which means the charge is located everywhere. And I want just to consider this part. Okay. So I want to calculate the charge included in the green region. This charge, I know it is negative. I will call it minus Q prime, right? So the total charge included in the whole green region is equal to the charge included in the part of the shell, the green part, plus the charge on the conductor. Do you agree? Now I want to calculate Q prime. What is Q prime? Q prime is the charge enclosed in the green region, of the insulating shell. How do I calculate Q prime? How I calculate Q prime? I know that rho is equal to minus Q divided by the volume that we just found, minus 3Q over 28 pi r cubed. Let me remove this first, so not to confuse you. Okay. I know that rho will be equal to Q prime divided by any volume prime. This is volume prime. Are you following? I want to find Q prime. I want to find the charge enclosed in the green region of the insulating shell. This green region has a volume that I call V prime. And the volume V prime, I know that it's equal to 4 pi over 3, okay, r, small r cubed. Are you following?
Yes, Professor.
Okay. Okay, so, okay. Any mistake here? I need V prime, I need to subtract for 3 pi r cubed, right? Right?
Because you need to subtract it from the original one.
Yeah, exactly. So this is the volume V prime. And that's it, I have everything. So I know that Q prime will be equal to rho V prime. And then all what I have to do is I know that the Gauss law is equal to Q minus Q prime divided by epsilon 0. And I know that Q, well, I know Q is given, minus Q prime is rho V prime that I found here, divided by epsilon 0, right? Now, what is the integral over dA? dA is the surface of the green region. And I know that this surface will be equal to 4 pi r squared, small r squared. This is equal to Q minus rho V prime over epsilon 0. Now, the electric field at any point r will be equal to Q minus rho V prime over epsilon 0, and then times 4 pi r squared. Any question? Any question? Okay. Now, okay, so we solved the problem here in this region. Okay, in this region between R and 2R. Now, what will be the electric field when R is bigger than 2R? How can I calculate it? Hello? Are you following?
Yes, Professor.
Shad, is not necessarily. You need to go, well, I would go, you need to go for the Gauss law also, right? You need to go for Gauss law. Now, Gauss law might give you this, yes, but you need to go for Gauss law. Now, what is Gauss law? Gauss law is the following: the integral dA, the charge, the total charge enclosed divided by epsilon 0. Okay, so if I go back here and I take this, so I'm going here. I want to calculate the electric field at this zone R. What is the enclosed charge? What is the total charge inside this system? This sphere, green sphere? Exactly, 0. Because I already gave you in the first point, in the first question, find the value of rho so that the net charge of the entire system is 0. So the net charge is 0. This means that the electric field at this point outside this system is equal to 0. Any question? Any question? Is this clear, please?
Yes, Professor.
Can you see my screen?
Yes.
For some reasons it says it's paused. Okay, I will. Okay, so I will just reshare it again because it says that. Is it? Where is this? Ah, yeah, it's here. Okay. Now, here is the question. Calculate the potential difference between the surface of the conductor, where R equal R, and the surface of the insulator, where R is equal to R. Remember, again, we have the conductor, and then we have the shell. And I want to calculate, so this is 2R, and this is R. And I want to calculate the potential difference between these two parts. Okay, how can I calculate it? Any idea? I want to calculate the potential difference VR minus V2R.
Do we integrate the electric field?
Exactly, exactly. Very good. Yeah, yes. You integrate the electric field. Yeah, exactly. You integrate the electric field R to 2R E dl or dr. Okay, and we have already calculated dr here. In here, so we have already calculated this. No, what is it? No, yeah, here. All what you have to do is to integrate over R. So you will have a logarithm there. I mean, you can do it at home, but I just want to go. Please remember this. This is a very good answer. Any question? So those are the type of questions that can come. I mean, we can reverse. We can say, okay, I have an insulating sphere here. Now it's an insulating withdrawal. And then I have a shell, a conductor shell inside with a charge Q. Okay. And then you have to determine the Gauss law at different regions. So those are the questions that you can have. Well, let's go to another question. This one. Two small charged objects, each with mass m and charge q, suspended, each with a wire length L. Okay. When the charges are in equilibrium, both wires will have an angle theta with the vertical. What is the tension of each wire in equilibrium as a function of only the mass, gravitational strength, and theta? Justify your answer with the diagram. Now, again, let's go to the keyword. This is very important to look at the keyword of your object. Two small charged objects, we are talking about charged object. They are given the mass, the charge, and they are given the length L. This is L. Okay. When the charges are in equilibrium, this means that they have the same charge. Okay, they have the same charge. They will exert on each other the Coulomb force. They will repel from each other, and the idea here is what is the tension of each wire in equilibrium as a function of m, the mass, g, and theta. Any idea about this? Any idea how to solve this problem?
Is it going to be like the same way we solved in mechanics, where we find the sine and cosine and then we label the forces?
Okay. Who is talking? I could not see who is talking.
Me, Marwan.
Okay. Yeah, very good. Yes, it's a free body diagram. Okay. This is a free body diagram. So let's see. I know that this force, this object, they have three forces acting on them. Can you give me which are the forces acting on each one? For example, the one to the right.
There is tension and there is gravity and there is the electric force, which is repelling it from the other charge.
Exactly. So the tension is this, the electric force is this, and the gravitation is this. Okay, the gravitation mg, call it. Okay. Now, if I take the x-axis, this one, and the y-axis, you can easily see that if you do the projection of the free body diagram that you have learned along the x-axis, you will see that the electric force minus, so this is theta. So this means that this is this will be sine theta. So minus the tension sine theta. So this is the projection of T along the x-axis, sine theta is equal to 0 because the object is not moving. So there is no acceleration. Okay. So this is along the x-axis. Along the y-axis, along the y-axis, the projection is this. This is ty, and you can see along the y-axis it is ty. No, ty, which is t cosine theta, the projection, minus mg is equal to 0. Let me see if there is any question. Yeah, no, there is no question. Okay. So this will give that the tension is equal to mg divided by cosine theta. This is exactly what they were asking, mg and theta. Any question? Okay, so now we need to calculate the charge of each object if the angle theta is 30 degrees, the length is 20 centimeters, and the mass is 10 grams. Now we will go to the charge. So now for the charge, I know the force is equal to K. I will, for 1/4 over 4 pi epsilon 0, I will just put it as K. Okay, so the tension is already did. I already did it. The tension is here. The tension, what is the tension of each wire in equilibrium as a function of m, g, and theta? So I already got m, g, and theta. Okay, so now I want to calculate the charge. Given that now they are giving me the mass, the length, and theta. The charge, where is the charge? The charge is only included in the Coulomb force. Yeah, yes. So I will do it later. But for the moment, let's calculate the charge. They have the same charge. This is Q squared divided by R squared. What is R squared? Now, R squared, I will put it in green. R squared is this distance. This is R, distance between two. Now, remember that sine theta of this angle is equal to R over 2 divided by L. Sine theta is equal to R over 2, the half of the distance, the opposite side, divided by the hypotenuse, which is the length. Okay, so this means that R, the distance between the two, is equal to 2L sine theta. 2L sine theta. Okay, so I know that from this equation that the Coulomb force, Q squared over R squared, is equal to T sine theta. And I know that T sine theta is already given. I already found the expression of T, which means mg and then sine theta divided by cosine theta, which means mg tangent of theta. This is the expression of the charge, sorry, of the force. Now I will continue here because I don't have enough space. I will continue here. So K Q squared over R squared. What is R squared? R squared is 2L sine theta squared is equal to mg tangent of theta. This means that Q squared is equal to 2L sine theta squared tangent theta divided by K. So this means that the charge in each object is equal to 2L sine theta if I go to the square root, and then the square root of tangent theta divided by K. Okay. Any question? Sorry, mg. Here I forgot mg. Yeah. Yeah. No, it's a mistake. Yes. It's mg. Yeah. Yes, mg. I just thank you. Yeah. So here it's mg. Let me just okay. So this will be mg tangent theta, and this will be 2L sine theta, and then mg tangent theta divided by k. Of course, here all what you have to do is to convert L must be in meters, and k is given. The mass must be in kilogram, okay, and g is given, and theta is in degree. Any question? Any question? Okay. Let's go to problem 3. An alpha particle at rest is put in a potential drop, which means potential difference, and the charge of an alpha particle is positive and equals in 2e, which E is the charge of the electron. Now, remember, we have a charge that is equal to 2 times the charge of the electron, and the mass of the alpha particle is given, okay? And it is accelerated over a potential difference of 10 to the power of 6 volt. What is the kinetic energy in joule and in electron volt? Any idea? How do you solve this problem?
We'd have to use the equation,
Which
the work energy theorem equation, yes.
Yeah, exactly. The work energy theorem. Yeah, the work energy theorem. Very good. So the work energy theorem, because remember the particle is at rest. So the work energy theorem tells me that the final energy minus initial kinetic energy is equal to the work done by the electric force, which is the charge times delta V. In this problem, I have 2 times the electric charge, 2 times the charge of the electrons. So the final kinetic energy is equal to 2E delta V. And then you have to do the following. Either it will be equal to 2 times 3 10 to the power of 6, which is 6 mega electron volt, or you multiply by 1.6 10 to the negative 19, and then 3 10 to the power of 6 to find it in joule. I think I have value, yes. It's 9.6. It's 9.6 10 to the negative 13. Any question about this? This is a very easy question. Did you understand what I did? So all of you knows that this problem has to be solved with the work energy theorem. Okay. Now, please remember, whenever, and because sometimes in the future, when I ask students, okay, how do I accelerate? Let's say, for example, I have a charged particle and I want to accelerate it. How do I accelerate it? Very, very easy way. Okay, so we always accelerate particles by putting a potential, the particle in a potential difference, which means the charged particle, it will be subject to the electric field, to the force, and it will be accelerated. So what is its speed? It's a very easy question, because now we have found the kinetic energy, which is already found, so we can easily find 2k over m and then the square root. Okay, so this is the kinetic energy. Obviously here you have to use the kinetic energy in joule, not in electron volt. Okay, you have to use the SI unit. By the way, this is not this question is not included because we are not including chapter 25. So this question, and then we can go to question 5. Okay, so so the electric potential in a regions of space is given by this value or this expression, where A is a constant to be determined later. Derive the expression of the electric field in this region. If I give you the potential difference and I ask you to calculate the electric field. Exactly. So E is the minus the gradient of the potential difference. And I already give it. So this is given here in the first page. Okay. So what is the expression here? Yeah. So the electric field. Okay, so the electric field will be equal. Remember, the electric field is a vector. The potential difference is a scalar. So it will be minus the partial derivative of the potential with respect to xi minus the partial derivative with respect to y along the j or the y-axis, and minus the potential difference, the partial derivative of the potential with respect to z along the z-axis. And of course, you will easily see that the difference with respect to x will be 2ax I with a minus sign, okay? And with the difference with respect to y, it will be minus 6, so it will be plus 6yj, and then a, of course, a, and then the minus 2azk. This is the electric field. Any question? Any question? Okay, so here, this was a little bit, I would not say a tough question, but this was a question. Sometimes I give a question that really test the deep understanding of the student. Here, the question is the following. The work done by the electric field when a 1.5 microcoulomb charge moves from point 0.25 to the origin is measured to be 610 to the minus 5 joule. So what is the value of constant A? So the question here, if let's say I have a point 0, 0, which means x is equal 0, y is equal 0, z is equal 0.25, and I want to move this particle to this. When I apply a discharge particle, this electric field will move this charge from here to here by doing a work, or the force, its force will do work that is given. So I want to calculate the constant A. Any idea how I do it? I can do it.
I think we'll first try to organize the equations and what we have, and then we will try to see what we can do.
Yeah, so which equation?
We can use the equation work A to B equals the charge multiplied by the potential difference.
But here, this is really what I wanted to, why I gave this question. Remember, the electric field here is not constant. It's changed. The electric field here, if you look at it, changed as a function of x, as a function of y, as a function of z. So you cannot apply the rule directly. So you have to apply the general formula of the work which is the integral, okay? So the work to go from point, I will call it from P to the origin, is equal to the integral, where you go from P to the origin of the electric force, Q, E, dl, right? Did you understand? I need more space, so that's why I want to have another page. So what I want to do, I want to move a charge from point P to the origin. So the work done to move from P to the origin is the general formula. The work done by the electric force is to go from P to point P to 0 of the charge, the force, times dl. Okay? Is this clear? Now, what is, I know that E has EXI plus EYJ plus EZK. And I know that dl is equal to dx. Dl is the integration element. So it has a displacement, an infinitesimal displacement along x, plus an infinitesimal displacement along j, plus an infinitesimal displacement along k. So when you do E dl, this is a dot product, you can easily see, and we have seen this in class, it is equal to Ex dx plus Ey dy plus Ez dz. Now let's do it here. So this means that this is equal to the charge and the integral when we move from point P to 0, and Ex dx plus Ey dy plus Ez dz, right? Any question? Are you following?
Yes, also, Professor, I think you wrote the z coordinate for the point wrong. Isn't it supposed to be 0.25 for the z of the point?
This one?
Yeah, the z coordinate of the point.
Yeah.
in the
So
que-
this is 0, 0, 0.25 to 0, 0, 0. Did you understand this?
Yeah.
Because we are moving from point P, which has coordinate 0, 0, 0.25, to the origin, which has coordinate 0, 0, 0. Is this clear?
Yes.
Now, remember, the only displacement that is happening is along the z-axis, because the x-axis does not change, and the location of the y-axis does not change, right? According to this example. So the only displacement will be along the z-axis, okay? And then, so we can easily integrate from 0.25 to 0 of Ez dz. And what is Ez dz? We already calculated it before. Yeah, so this is minus 2Az, okay? So I can go back, minus 2Az. Up here. Yeah, so it is the Q and then times minus 2Az dz from 0.25 to A. Okay, I can do it minus 2AQ, the integral from 0.25 to 0.0, okay, to 0.0 of what? Of z dz, which will give me minus 2AQ, and then z square over 2, z square over 2, with 2 it will go. So from 0.25 to 0, this will give me minus 0, so it will give AQ 0.25 squared. And this is equal to the work that they gave us, 6 × 10⁻⁵ joule, okay? This is equal to 6.10⁻⁵ joule. This is the work. This is the work to go from point P to point origin, and you can easily, we have already the charge, which is 1.5 microcoulomb, so I can get the constant A. Are you following?
Yes.
Okay. So this is a question. Sometimes I give this kind of questions to test the understanding of students. Okay. Yeah. So of course, what is the magnitude of the electric field at point P? How can you do this? What is the magnitude of the electric field? So the magnitude of the electric field will be EX squared plus EY squared plus EZ squared, right? Squared. And we have X is equal to 0, Y equal to 0, and Z is equal to 0.25, because this is what the point P. Those are the coordinates of point P. All what you have to do is to replace here, Okay? So X will go because there is no, yeah, so the X is equal to 0, it will go. Y is equal to 0, it goes. And what you will have to do is 2AZ squared, so the absolute value. So we already calculated A from the previous question. Z is equal to 0.25. Any question? Is this clear for everyone?
Yes.
Okay.
Yes.
So we go to the last problem, which is the capacitors. Now, here, again, for the capacitor network shown in the figure below, a potential difference across point A and B of 12 volt is applied. So now they are giving us the potential difference across point A and B. What is the equivalent capacitor of the whole circuit? How would you do this? Now, please, if you have this question, if you have this kind of question, I really would like you to do the following. For any problem, you have to specify, okay, for me, let's say I want, you can say, okay, this is C1, this is C2, this is C3, this is C4, and this is C5. What will be your first step?
But
Find
first
which-
analyze and see what we have, either parallel or either we'd have them in series.
Okay, so which one are in series?
C1, C2,
So C1 and C2 are in series, and then
C3, and C4.
C3 and C4. Yeah. Okay, very good. And obviously, C3, C4 are both in parallel as a whole with C5, right? So, and then what I would do, I would go for taking care of these two in series. I will call, okay, again, if you remember, I gave you sometimes there some students they do the same mistake. So how do I know that if I call C1 C12 is the equivalent of C1 and C2. So then, because they are in series, C12, 1 over C12 will be equal to 1 over C1 plus 1 over C2. And then you can easily get C12. Now the circuit becomes C12, and then let's go, this is C5. Again, for C3 and 4, I can also do the following. 1 over C34 is equal to 1 over C3 plus 1 over C4. So this is C34. Okay. Now the next step will be to see that C34 and C5, they are in parallel. So they are in parallel. This means that the equivalent here, which I will call it C345, will be the sum of both of them. And then my circuit becomes C12 and then C345. This is point A, this is point B. And then 1 over the total, the equivalent, will be 1 over C12 plus 1 over C345. Are you following?
Yes, Professor.
Yes.
Okay. So this is how, now, as I mentioned, please do not do this mistake. When I give you let's say this is C1 and C2, okay? Several students, they do this mistake. Let's say this is 1 microfarad and this is 1 microfarad, for example. What is the equivalence capacitor? The equivalence capacitor is is equal to 1 plus 1 over 1, which is 2. So the equivalence capacitor is not 2. They forget to flip. So the equivalence capacitor is 1/2. Please don't forget this. Many students, they do the same mistake. In the series, don't forget to flip. Because sometimes you are happy that you found the 2, and then you said, okay, C equivalent is 2. No, it's not 2. You have to flip it. Please don't get this mistake. Because it just, you can see that it will just give you the everything wrong. What is the total energy? Now the total energy, how do I do the total energy stored in the circuit? Total energy. How can I calculate the total energy stored in the circuit?
There is an equation you taught us in the class. Yes, that's
Okay. So I already find the equivalent capacitor, and I know that the potential difference is given between A and B, which is 12 volt. So 1/2 the equivalent times 12 squared. Okay. Yes, yes. I mean, yeah, you can find the charge, you can find. Yeah. The last question is, what is the energy stored in the capacitor? So here I want to calculate the energy stored in capacitor that is in 4.8 microfarad. Now, let's go to this circuit. Yeah. Okay, so let's just explain something. I have, this is A, this is 4.8, and this is, I think, 8.6 microfarad, and then I have this, and then I have this, and this B. Now, I want to calculate the total energy stored in this capacitor. Well, remember, the charge that goes through this is the same charge as the one that goes through the whole circuit. So the charge that goes through, because the charge starts from here, this is the total charge. So it goes through, the same charge goes through the 4.8 microfarad. When it comes here, this charge will split, but the initial charge will go through this and this entirely. So this means that the total charge will be equal to the equivalent circuit, the capacitor times the potential difference across AB. It will be also equal to the capacitance 4.8 times the potential difference 4.8. Potential difference 4.8. This is 4.8. And what I want to calculate, what is the energy. What is the energy stored? I know that the energy stored in 4.8 is equal to 1/2 the capacitance, which is already given, times the potential difference across the capacitance, the capacitor 4.8. I don't know this, but I have this formula. And this, I already found it. This is given, this is given. So I can easily isolate this. And then I will get the potential, the potential energy stored in the capacitor C4.8 is equal to 4.8 times this potential difference, which I can get from this equation. It is equal to C equivalent VAB over C4.8 and everything squared. I have now everything. It is equal to 1/2. I can get rid of this and this. So it will be C equivalent potential difference squared divided by the 4.8. I have everything. I have this, I have the potential to 12 volt, and I have the value of the capacitance, and this will be in Joule. Any question? So please, please, please remember that this is the key point, is that the charge that goes through this capacitor is the same charge that goes through this capacitor, is the same charge that will be circulating in the total equivalent capacitor. So if the initial charge that is coming here is the same as this charge that is going through the total across A and B, the same charge. This is the solution for this problem. Otherwise, you cannot do it. Okay, so I will stop here. Those are the type of questions. Now, I might tell you, for example, okay, understanding questions. What happens to if I C4.8, I included a dielectric inside. So what happens? Do we have a capacitance that increased? Do we have more energy, less energy? And you have to explain. By the way, I will give you the formulas. Yeah, the formulas for the capacitors I will give you. Okay? Any question? I will stop here, but if you have any questions, you can send them to me. For the exam, please remember, you have to bring your calculator, and that's it. It's a closed book exam, just a calculator. We will give you, well, of course, calculator and a pen. We will give you scratch papers, and we'll give you, of course, the exam papers. That's me, yeah.
Professor,
Okay.
it will be
Wait,
the
wait.
same room, right?
Wait. Someone is asking me to go up. I don't. Who is this? Yeah. Yes. 8.6 and then 4.8. The question was to calculate the energy stored in 4.8, right? Okay, tell me which one you want. This part. Okay, part C. This one? Okay. Okay. Do you want me to go down? Okay, so then I will stop here and see you, inshallah, on Sunday. If you have any questions, just tell me. Thank you. Have a nice day.